So I guess all of you have seen, but the exercise set 2 is published. Remember, I'm not the bad guy. You have to practice. If I tell you stories here, you say, oh yes, I understand. You go home, don't practice, you forget it. Okay? You have to practice. So the idea of the exercise is part of the learning. What is taught here in class, what you think you understand here in class, you're going to test it in the exercise. And part of the learning, part of trial and error, making mistakes, is happening when doing the exercise. Okay, so it's not, and also the plus side is it accounts for your grade. So is a similar case that we did on exercise set 2 is exactly the same field, this Snow White, Snövit. But now we want to go further in the analysis. It's not only computing production profile, but the main task is to determine what will be the number of wells and the field plateau rate. We know we want to operate in plateau, production A, and then decline. And we got some intuition. This is a remote field, it's a standalone field, so we think, from what I have told you, that it should be produced in mode A, okay? Plateau mode and then decline. So you have to find these two using something. One of the things, there are many things, recovery factor, production, but mainly you use some economic value indication, okay, indicator. That's what you use to compare different alternatives. You can use many other different things, technical part, but at the end, the final decision, you use some sort of economic indicator. Okay, and that we are going to cover today slightly. Okay, but the first step to calculate, so we will see now this procedure involves summing expenses and summing revenue. To compute revenue, you need the production profile. That's the biggest and most important input for this economic calculation. So that's part of the task. So that's the main task you have. You have to define what is the best that gives maximum economic value. And I recommend to use an indicator called net present value. How many of you heard about NPV before? Many of you? Okay. So I don't have to repeat too much. And then to make it more robust, your decision analysis, you have to do some very simplified sensitivity on this, what affects this indicator. So I try to guide you on the questions, guidelines, that you should first compute the production profile of each one of these cases. And you decide how many wells. You're a bit free to decide on that. Okay, but I gave here a range. I say, well, the number of wells should be between 6 and 15, and the plateau rate should be between 20 and 35. But you decide. You have to test every combination. If you decide to use 6 wells and 20, you have to go compute the production profile and then see how it performs. So one thing here, we are not going to use the simplified calculation. If we make a sketch of our system, we have what we call a PLEM pipeline entry module. It's like a place where we commingle the production of different wells, different templates. And from there I have a long pipeline, 150 kilometers, all the way to shore. Yeah, and here I have, in each one of them, I can have maximum 3. So I taught you last class, I told you how to make this equilibrium calculation to find rate, but based on a single conduit. If you remember, the case we had last class was a simple well, single well. Okay, we had a pipeline, and then we have a separator. And that we know how to solve, right? You already know. But how do I tackle this more complex system? We are going to discuss, let's see if we have time, how do we deal, this is what we call a network. Okay, this is called a commingling, I think it's with 2 M's. or gathering network, where the function is we commingle the production from different wells and take it to process, okay, take it to shore. But here we have a very special case, okay? If we say that all wells are identical, and the other assumption is that all templates are symmetrical, actually it should be symmetrically positioned with respect to plem. That means that they are, the length of the pipe is the same, the location of the pipe is the same, the elevation of the pipe is the same, everything is the same. And one more thing, there is the same number of wells in each template. Okay, a lot of assumptions on each template. So then you can make the assumption that first the rate of each template, Q template, let's put TE, Q template, and Q template, they are going to be the same value. Because all wells are identical, the templates are symmetrical, so you can say they are all the same. Here I have Q of the field, here I have Q of the template, which simply will be Q of the field divided by 3 in this case. And then I can say that the rate of each well is also the same for all wells. After, that's just to make your life easy. It's your first calculation with flow equilibrium, so we have to reduce a bit the complexity. Later, when we talk about networks, we can make things more complex. Okay, but for now, so that means that if you look at this branch, pipeline, template, this well, or you look at this branch, pipeline, template, this well, they should have exactly the same pressure along the pipe and exactly the same rate. So it will be equivalent to look at any branch. Okay, so let's say I pick this one. So it's the same to look at this branch, for example. Okay, that will be branch 1. All branches are identical. And if you see I make a plot of that, I end up with basically the same system that I had in the previous case, what that we have done in class. We have this piece of pipe, which is, I call it a flow line, and then we have this piece of pipe, which is a pipeline, and then we have the separator. So we have P separator, P plem, pipeline entry module. We have here P at the template. Of course, we have here an element which is called a choke on the wellhead. Then we have here P wellhead and P WF. But be careful, you have different rates in every conduit. In this conduit, in this system from here to here, you have Q of the well. In this system from template to flow line, you have Q of the template. And in this system here, you have Q of the field. But all of them are related, right? The Q of the template is simply the Q of the field divided by the number of templates. And the Q of the well is simply the Q of the field divided by the number of wells. So if I fix one, all others are defined. Okay, so basically you have the same system and you can do exactly what we have done in class. Okay, we fix a point. In our case, our point of interest will be here, upstream and downstream that element. Calculate the pressure available before that element, the pressure required before that element, and then we see if the available is greater than the required, I can produce the rate. If the available is less than the required, I cannot produce the rate. Then I have to change the rate. Okay. So that's the approximation you have to make, and the first step is to compute production profile. It says you have here is explaining what I have explained now. Let me open the Excel sheet. So all equations, I think last class you programmed them manually. Okay, so all equations that you need are, if you press Alt F11, you will find it in flow equations, and you have all the equations programmed, so you don't have to program yourself, or you don't have to put the numbers in the cell manually. Okay, so here you have tubing equation when you have the rate cleared, when you have pressure 1 cleared, or when you have pressure 2 cleared. So please, I say, use the BBA function. And the main reason for that is that if you program this equation, or if you write that equation directly on the cell, okay, let's say you are here and you're calculating from reservoir pressure Pwf. Okay, you simply want to say that is the rate of the well divided by the C. Okay, then I square that, and then I say PR minus that pressure, right? PR squared minus that, and then all of that. Okay, that's the back pressure equation that I'm using, to the power of 0.5. Okay, sounds simple, but I can make a mistake. Potentially I can forget a parenthesis, I can forget to divide, I can do something, and then it will be very hard to find the error. Okay? And if I need to apply that equation any other place, also I can have another error. So by using a function, I make sure that this expression should be correct. And if I find an error in this expression, when I correct it here, it's going to be fixed every place where I call the function. Okay, so I just try to encourage you to go away from typing a long equation on a cell. Okay, try to use the BBA function. What else? So here you have, I would say you have to compute from reservoir pressure to so let me just take a copy of that. So you have here all the equations you need. Okay, so here you will have to compute from PR to PWF. You use here the IPR equation. From PWF to PWH, here you use the tubing equation, and you stop. Okay, you fix the rate, you go from the bound, from reservoir, bottom hole, wellhead, you stop. And then you move from separator to PLEM. Okay, this is the pipeline equation, and we are going to assume horizontal pipe. Then we move from here to template, and that will be the flow line equation, which is the same as the pipe with another C. And finally, I compare these two. If this one is bigger than the other, then I can flow. If that one is less than the other, I have to reduce the rate. Okay. And here you report the delta T of the choke. And you do that year by year. You already know how to make the part on the predicting reservoir pressure. You need C, you need the recovery factor. Okay, so that part you already know how to do it. And then you have the rate of wells shouldn't be more than 3 million. Also, when you want to change, let's say you want to use 7, okay, then you will lose symmetry. If you have 7, let's say you can put 3 and 3, but if you have 7, you will have to put 7 templates, okay, or yeah, maybe 7. You have to find a way that you have symmetry, such that you can just look at one conduit. You can just look at pipeline, template, and well. So be aware of that. The way I write it here is that you should have the same number of wells in each template. Okay, I'm giving here a cost. We are going to see now in class how do we have to sum all of these revenues and all of these expenditures in one single number that gives me the value of the project. Okay, we have to compound all of that in one single number. So the well cost is $100 million. The manifold, if you have to add manifold when you put more wells, is 20. The main pipe that goes from here 160 kilometers to shore, that is fixed for all cases, is $500 million. And then the cost of the LNG plant, the plant that you have here to receive, I think here there is a picture. That plant is placed on an island called Melkoja. And that plant has a cost depending on how much you are producing. Okay, now we are here using a very simple function, which is like a straight line, where it's simply $160 per standard cubic meter per day. So depending on the rate of the field that you choose, that gives you the capex of the plant. And one more complexity is the LNG carriers, okay, that you need to carry. Remember here in this plant, the gas we converted to LNG, liquefied natural gas, which is like a liquid, is like oil, and then we ship it to the market. But we have to have something to ship that production to the market, and that we do with this LNG tanker. Okay, so here it tells you the number of tankers will depend on the production that you have. Okay, so if you have higher production, you need to transport more often, and then you need to have more tankers. Each tanker can make only 22 trips per year. Okay, it's a lot of information, but you know, when you start doing it, you can come back with questions. Okay, and here there are some. And we have another that I think this one you can solve with the information you already have. Any question before we move to the next topic? No? Okay, so this has deadline, I think is in 2 weeks. So I think that's going to be on the 13th of February. Yeah. Okay, so now let's talk about something that we discussed last class. Okay, we said our system, our simple, very simple dry gas system, PR, PWF, P wellhead, then I have this choke, then I have a pipeline, and this I think we call PDC, downstream of the choke, and P separator. I told you that basically there are two ways to model that system. Okay, two ways that we can compute the production profile. Okay, one way is to remove the element that I can control, the element that I can change, remove the controllable element. Okay, so let's write here just title. Okay, remove the controllable element and compute the available pressure upstream the element, available pressure curve upstream, and then you have to compute the required pressure curve downstream. Okay, actually you don't need to compute the curve, all the curve, but you need just to compute the available pressure and required pressure. You can just do it for the rate that you want. Okay, but graphically, if I graph here pressure versus rate, I have one curve that looks like that. That's the curve from reservoir here. And you have one curve that looks like that. You compute for the rate that you are provided, Q star, the pressure upstream and the pressure downstream. And I say if delta P, if positive, then the rate is feasible. Or if delta P is less than 0, then the rate is not feasible. And then you have to make equilibrium, right? You have to find exactly where that intersection is. And then you have some solving process. But if not, if you are in this case, simply you say is feasible, finish. I move to the next time step. Now, what is the second option, second modeling option we have? And that's the typical option that you have in many simulators. They use this option. So you have to be aware. That's a simple way to do it, and I think it's the easiest to understand. But the simulator is using another option, which to my opinion is more complicated. But if you're going to be working with simulators in the future, you have to understand that they do it this way, that I'm going to show you. So the option is include the choke model. They include the equation of the choke. That means they have, let's list the equations we have. QG CPR squared PWF squared to the power of n, the IPR equation. Then we have the tubing equation. Then we have the choke equation, which I need some help here to see what is the choke equation. This is P2 over P1 okay, this K doesn't go here. Oh, this K maybe. And you have one more equation in our case, which is QG is C flow line P DC, right? So here is not P2 or P1, but it's basically DC over wellhead, and this is wellhead over DC. And finally we have this equation P separator to the 0.5, right? These are all the equations that I have to solve. The IPR, flow in the formation, flow in the tubing, flow through the choke, and flows through the flow line. So how do I perform? So the simulator, what it does the following, okay? It assumes, so it knows beforehand the Q target. Like that we know here, right? We know this Q star, okay? That's a rate that you know. Q target is Q star. That's the Q that I want. Now I assume a choke opening, and the choke opening comes in this equation here. This A2 is A2, and you can take any number from the fully closed to fully open. Okay, they start maybe with fully open. Assume choke opening, and then solve the system of equations. Okay, so that's the first step. The second step is solve the system of equations. And then the third step, they compute a rate, right? They compute a Q. So the result is a Q1. Then the fourth step is compare, is Q1 equal to the Q target? If that is correct, then that means that I have A2 is the solution and the rate is feasible. Okay. If not, then I have to go back and assume another opening. Okay, so I have a system of equations. I don't know, I'm not sure about, let me put it a bit like that. I have a system of equation, and this guy can change from fully open to fully closed, this area of the choke. So I say, I want this rate. That's something that I gave. I want some target rate. I assume the opening, solve the system of equations, all of this, which is very challenging, especially because of this ugly equation that has a lot of things. Then I calculate Q1, and then I have to compare. Okay, is this Q equal to what I want? No, then I have to assume another A. If yes, that means that I found a solution. Okay. Yes?
Is A2 between 0 and 1, or is it the area?
Is the area. Okay. These are, that you can see on the compendium is explain what is each thing. So this is area in, so that is basically, that's a very good question. Okay, so this is A1, and this is first diameter 2 and diameter 1. And even though not all chokes look like that, that's all choke models are made on a big area and then to a small area. The transition between 1 and 2. So area 2 will be pi, okay, P2 or 4. Okay, so this one you regulate basically by closing or opening the valve. If we go on an analog that I mentioned last class, you have something like this. Okay, so that area will be basically this small area that I have here. Okay. So you have, keep that into account. So to make this, you see here I have one solver, okay, which I might use Newton-Raphson, but here I have another solver. So I have a solver on top of a solver. Okay, I have to solve two equations sequentially. I have to find with this one and then solve the other. I have two loops. Okay. So this is an iterative process. Let me write it here. Iterative process. Okay, this is sometimes called in commercial software network solving. Okay. And this step here that I have, this big loop, is also an iterative process. Okay, from 1 to 4 is also an iterative process. And this is often called optimization, which is not correct. Okay, it's not the right term, but people call it optimization because you're trying to find exactly the A that gives you that rate. Okay, so just be aware of that. In this course we are going to work mainly on this procedure number 1. I think it's much easier. You just come in each equation, okay, the IPR, you can calculate from there the PWF. Okay, simply by substituting PR minus Q. Okay, then you go to the tubing equation, to the flow line equation. You can clear explicitly the variables that you want. Okay. But that's when you go to commercial software, that's what they use typically. Okay, and we are going to have maybe when we talk about pump, we're going to go a bit more to do it this way. Okay, but not much. I don't like to. If you do it in commercial software, that's fine. But to make it manually, it's well, we might, when we cover pump, we might review that. Okay. So now let's talk about something else. Okay. So in the field development process, typically you don't have like we have now. Okay. So far we have the reservoir simulator. Okay. Remember, if we say our tank approximation, okay, we are saying that's our tank, and then we have a restriction, and then we have here one Pwf. Okay. All of that is what we call our reservoir simulator. And production simulator in the same, let's call it in the same platform. Okay, we have it in the same tool, okay, in the same platform or the same software. Okay, you can call it software, or we have it in the same tool. Okay, the rest is actually we have a tubing, then we have our choke, okay. So far you haven't had, and then you have a pipeline which might be like that, and then you have a separator, piece separator. But also in the industry, when you go out and you start working on a company, the two things will be in a separate part of the company. Maybe you're sitting next, but you are in different department. Okay, this is typically maintained, created by reservoir simulation department. Okay, this is typically, so in the industry, typically is developed, updated, okay, and run by the reservoir simulation department. Okay. And this guy is typically developed, updated, and run by the production simulator department. Okay, I think it's important for you to, to know how we have, it's very simple. We have everything in the same Excel sheet, and we can transfer information between them very quickly. But in reality, that's what you have. You have two different departments, and here you might have these names that you have heard: Eclipse, you have Embal, you have Sensor. Okay, you have, what is the new one of Schlumberger? It's Intersect. Okay, you have OPM. You have this simulator by Syntef, MRST, etc. You have CMG. Okay, you have all of this software. Okay, and here you have, typically you have Gap and Prosper. You have PipeSim, you have Olga, you have LedaFlow, which are different tools that you have to make that calculation. So how do they, remember I told you always, the production profile is a result of both. You have to put these two guys together. You cannot take just Reservoir Simulator, you cannot take just Production Simulator, you have to couple both. So how does it work, the regular workflow to get production profiles? So typical workflow, industrial workflow, to get production profiles. Okay. First, the Reservoir Simulator they make runs in the reservoir department. And these runs they make by trying to optimize recovery factor. How do we increase the recovery factor? Okay, they find they have some goals. Increase recovery factor. So they are looking at where to place the wells that you increase recovery, well placement. Okay. Then you have pressure maintenance strategy, how I'm keeping the reservoir pressure high such that I can have a high production, pressure maintenance. Strategy. And then I look also at enhanced oil recovery. Okay, how can I get, if I have water injector, they will start to push oil towards the producer, and then I increase the recovery. And they, very important here, they assume, okay, a minimum Pwf minimum. Remember on the first exercise, that was one assumption you made, that in our case was 120 bar. Okay, but I have this very important assumption, I assume Pwf mean. With that they come, they are very happy, they have done all of their study, and they come and they have, with time, they have reservoir pressure, they have rate of the well, they have the GOR and the water cut. Okay, they have a table. So that's the result of the reservoir team. And that result goes to the production department, production. Okay, and remember these guys, they have the pipe, they have here an IPR, okay, and then they have the separator. And in this simulator, in this box, what they are basically doing, they are verifying the rates. These guys say, well, this is optimum. If I produce my field using this approach, life will be easy, simple. We found the solution. Now give it to production engineers, they will see if there is any problem. Production engineer come, they substitute every time in their model. And they find, here you have a problem, here you have a problem, here you have a problem, you cannot produce here, you cannot produce here. And they give instructions back. Okay, so here they come and they say, so they come here and how do we write it? So say rate feasibility. Okay, so let's copy the same table. Time, Q well, GOR, water cut. But now they add a small column, say feasibility. Okay, yes or no. And then they add one more, which is a solution. Okay, and the solution might be increase the rate simply or reduce the rate. Okay, increase Q or reduce Q. For every time, for T1, T2, T3. It's becoming very messy, okay, this process. But then they come back with that feedback to reservoir engineer that they were happy, they already found their profile, they are living life, drinking, having drinks. Okay, then come production engineer tell, well, 30% of your rates you cannot produce. No way. We have to reduce, increase, do this, do that. Okay, and then they have again to take that into account, make your calculations, and pass it again to the production, let's call it here department, and department. Okay? So why do we have to take many loops? Why cannot be just in one loop? The thing is that when you do a change in a rate in a given time, okay, it's going to affect all subsequent rates. So you might say it doesn't work in time 3, but it's going to affect, because you're draining less from the reservoir, so it's going to affect all other times. So if they adjust, they come back here and they run, now they have to check once more. And again the cycle is repeated. So that's why these two guys sometimes they hate each other. Okay, you're in the reservoir team, they hate production and they don't have lunch together. These are just pump guys, these are your pipe. Oh, these guys only think about rocks, you know, so they don't like each other. Okay, so let's take a break, and then we're going to see what tools we have to make that. And that's actually something you are doing now, or we are doing now, but we never thought about it. We can have a system where we can exchange information between the two simulators such that we get a much better prediction. Okay, and that means that is coupling these two simulators. Okay, so let's take a break first. Let's say 15 minutes, and we come back. Okay, so to avoid that situation where we have all of these forth and back, and just be aware it might take a few cycles to finish that process. Okay, it's like if you visualize, you have a system of equations here, and you have a system of equations here, and they should be converged together. But you try to converge them separately. So it will take a lot of iterations. You perform these simulations, assuming this is constant, and then you perform these simulations, assuming this is constant. So it will take a lot of iterations to converge. Also, another challenge is that during early phases of field development, usually we have no idea how the network is going to look like. Where are we going to place flow lines? How many flow lines there are going to be? What are going to be the distances of these pipelines? What is going to be the size? So mainly this part is sometimes neglected, even though it can have a very big impact on the production profile. When you perform exercise set 2, I see even though it's not part of the exercise, I will suggest very strongly you compare both results. And you will see they are going to be very different, the predicted production profile. Okay, so that we try to solve, we try to address that issue with what is called coupling. Okay, trying to couple reservoir and production simulators. And you are going to see this is the process that you are going to have to make in exercise set 2. So in Reservoir Simulator, at time 0, P reservoir 0, I transfer IPR. IPR, remember, is a curve that tells me rate versus PWF. Okay, can be a straight line, can be curved. I transfer. In the production simulator, I have my network model that is taking those IPRs, okay, and it's also taking the settings of these adjustable elements. Okay, so it can be choke settings, or if I have a pump frequency, rotational speed. Okay. And after that I obtain the rates, okay, Q of the wells and Q of the field. After I have those rates, I go back to the reservoir model to transfer the rates. And PWF. Okay, and then the reservoir simulator will execute one step to the next time step. So you have here, I don't know how we make it, reservoir model, and it goes from time 0, it goes and compute. So that's compute, and then compute, and then it computes here the new at time 2, the new PR, and the new recovery factor, etc. And then you simply repeat. Okay, then you transfer once more IPR, okay, and the process is repeated. And if you see that, if you see the Excel sheet you have to solve exercise set 2, that's exactly in a way what you're doing. Okay, you are here first calculating the delta P of the choke and say, well, it's positive. That means I can move to the next step. I can assume that the rate remains constant during the step, and I calculate the new reservoir pressure. It's exactly the same. But here, so if I have a tank model, we can do it like that. Okay? But if I have a more complicated 3D reservoir model with all the cells and all the details and all the geometry, it's going to be exactly the same. Okay? So that is an example, okay, of a coupling strategy example. But also, this is an explicit strategy. An explicit, we call that, if you see here, these rates, actually they are only valid for time 0. For time at 1, okay, this should be time 1, they are not going to be valid. Or probably might be valid or not, but probably are not going to be valid. Okay, so if these rates, so you can have like that's explicit because let's write it here to see GP or NP between T0 and T1 is calculated assuming that QWI1, that this rate, okay, 0, and this Q field 0, is constant from T0 to T1. And that's why it's explicit. We make it such that you don't have to recalculate. If not, then we should have to repeat the step, the reservoir simulator step. We have to repeat now with another rate until we converge on the rate. Okay, and that's called an implicit. But don't be too concerned about that. So let's put here for an implicit coupling, the reservoir simulator step must be rerun, okay, until, because you cannot assume the rate is constant on the interval. But just to give you a tip, something is typically an explicit coupling with small time step, delta t is equivalent to implicit coupling. Okay, which is a good thing. I can choose, if I don't want this effect to be very huge, I do it every month or every week. I choose a very small time step to make this coupling. Okay, to avoid having an implicit coupling. Okay. And when this complexity of these two simulators change, okay, now we are using Excel, so we can have both in the same platform. but you are going to be probably using Eclipse, and you're going to be using PipeSim. And here you have to pause the simulator. The Eclipse has to stop, send information, wait for information from PipeSim, and then Eclipse can continue, and then has to stop. So the simulator has to have the capability of doing that. Okay, of stopping, getting new information, running, stopping, getting new information, and running.
Excuse me, are there any reservoir simulators that does this automatically, or a simplified version?
Reservoir Simulator, they have a way that you can use, you can put a network using tables. But I don't think there is any simulator that has both. You can have a company that has both simulators, but I don't think there is any simulator that has both. Maybe one from Landmark, or the son of Coates, Brian Coates. He has a simulator that has the two things, which is important. Okay, if you had the ability to put the two things on the same simulator, will be a great saving. But the thing is that, remember, these are two guys, don't talk to each other. They are sitting on, they sometimes hate each other, okay? So to couple, just I want to give, so commercial software to couple reservoir production models. Okay, you have I think it's called IAM Aboset. Okay, that's by Schlumberger. You have IAM stands for Integrated Asset Modeling. Okay. You can have also, there is one, this we have here at NTNU. We are lucky to have a academic license. We have another software which is called Resolve that we can use also for the same purpose. And I think I'm forgetting one. You can also integrate using Pipeit. It's from a company here from Trondheim. Okay, but it's very difficult. This simulator on the left is used by a group of people. They have different targets. They don't care about pipe. They don't care about pump. They don't care about well, anything. They just care about porous media. These guys, they just care about pipe. They just care about pump. They don't care about porous media. So it's difficult to find a tool where they have both. But the performance of the field depends on both. Keep that in mind for your future. You tell one day when you are manager, ConocoPhillips or whatever, oh, this guy told me it's both. You cannot take one. Okay. Let's see now. The next part is value chain model. Okay, so let's go now back after we have taking that detour. Let's take to make decisions in the field development process. I have to establish, or the company establishes what is called a value chain model, the value chain model of the asset. Okay, to take decisions about the field development. The company establishes the value chain model of the asset. And I'm going to try to make it, even though it will take some time, to make what is included in that model. So very central, and almost the most important part is the reservoir. So we have to get an idea, and that's very technical, okay, that part. You have to get an idea what do you have in the subsurface. the size, the depth, you want to know the properties of the rock, the properties of the fluid. So for that, you try to use as much information as possible. So you have here reservoir, structure, and volume. Okay, you get that from seismic, you get that from the partly of the geologists, you get partly by logging, by exploration drilling. Rock properties, where do you get these from? Well, you have all kind of methods, right? But coring, you want to get, you take a sample and basically you try to find out permeability, porosity, whatever. Then you have the fluid properties, the PVT of the fluid. And I'm going to put here just the main things that are using as input. Okay, but basically rock properties, PVT, that also I have to take a sample of the fluid to know what do I have. And the volume, the structure, seismic, sometimes I use logging, sometimes I use exploration wells. Okay, and then after that I can make also with that, we have something that we use very much in the early stages, which is reserve estimation. And that we're going to do maybe in a few weeks. Okay, we haven't finished yet with the production profile, but you have to estimate how much you have in place, how much hydrocarbon, oil, and gas you have in place. Sometimes for this input, if you cannot run Reservoir Simulator, you have to take a recovery factor, a tentative recovery factor, RF. Okay, if your model is not detailed enough that you can run simulations, then you have to use, based on similar projects the company has had. Let's say this is an oil field, undersaturated. For those fields, we typically have this type of area. We typically have, let's say, 30% recovery factor. Okay, so they assign a number depending on that. Okay, next, after that, after we have the reservoir, and only after we have defined the reservoir, we come and we define the production system, what I call the production system. So initially, for example, you will have only that. You don't have much else. But then when you get more information, you're populating the size of your reservoir, you start to populate the production system. Okay, and in the production system, we have different parts. First, we have the wells. How are the wells going to be? The gathering system, okay, or what we call the network. Then we say the processing facilities. And then we have the offshore structure. Okay, here on the offshore structure, we have sometimes the input from the marine environment. We are talking about offshore field, so the marine environment. Okay, that depends. We are going to talk about that also later. But say if we are in a place where it's very wavy, the water height is very big, so you have some, that has a lot of impact on that. And also has a lot of impact on yeah, I didn't put it here, but it also has a lot of impact on the gathering system. So how do we make it? Sorry for that. You'll have to erase a bit. Because the subsea affects how I'm going to make my wells, my gathering system, so that also affects that part. Okay? And then we use all of that, remember, from the point of view of, we are very passionate, right? Petroleum engineers, we like very passionate about every box. But economists, managers, they just like one thing, right? To how much are we going to get out of it? So they care about one big box that we have here on the side, which is production profile. Okay. The production profile we compute first by knowing a bit about the schedule, something that I decide. This will be the height of the plateau, what we have done so far. So something called production schedule. Okay. Let's say that the company made an agreement with a customer to buy gas, and they want to have some particular amount of gas, so that will be the schedule. That's already predefined. And then I have coming in, now it's becoming a bit more complex, the reservoir, and also the production system that I have. Okay, to compute the production profile. What do I do with the production profile? Compute revenue. Okay, which is basically the sales of oil, sales of gas, sales of condensate, or if I have LNG, LPG, NGL, all of these products. Okay, now it's going to become, every year I try to make it easier, but yeah, there is no hope, I think. So let's try. What else do we need? That revenue goes to what? Goes to what we are going to discuss very soon, which is NPV calculations, net present value calculations. Or let's make it more general. Okay, that's one of the methods, but we say economic evaluation. So I calculate revenue. Remember, to calculate revenue also comes the hydrocarbon price. That comes into the picture. Now that is just the revenue, right? What else do I have to include in the evaluation? The expenses. Okay? The expenses then are given by, there are different types of expenses. One is called CAPEX. That stands for capital expenditures. And for the CAPEX, basically I have to get information about the number of wells, the gathering system, the facilities, and the structure. All the items that I have to buy. Okay? And we are going to go more in detail. I don't want to put it here because it will be very messy. So what is inside CAPEX? Just keeping in mind that we are taking input of the characteristics of each one of these systems. If I have so many manifolds, so many pipelines, so many wells, that's affecting this number. Again, this number ultimately goes to the economic calculation.
You also have the production data?
Not in CAPEX, in OPEX. In yeah, CAPEX is but it's basically to buy, design, and install one component. Okay, maybe also to place. It's everything that has to do with, for example, pipeline design, pipeline, buy the pipeline, manufacture the pipeline, transport the pipeline, and install the pipeline. Okay, so it's one expense you make, and you have to make it at when the field starts.
But you could have a increase in topics if you're in your processing plant. If you're building your processing plant as well, but I guess you assume just the same.
Yeah, they are affected by. Yeah, that's true. That's very true.
Like how many separators?
Yeah, we can maybe put that then here. That's very correct. You have to put that dependency here. Or yeah, maybe we can put it here. The profile is going to affect the decision on this part. Let's make it an arrow like that. Okay, I think I have an arrow like this. That's good. Okay, then we have Drillex. Okay, drilling expenditures. That comes also from the number of wells. Then we have OPEX. And we're going to see I'm going to list very quickly what OPEX, operational expenditures. Okay, and OPEX is taking into account how much I'm producing, and also is taking into account all of these expenses. And finally, I have is ABEX, which are abandonment expenses. Okay. And here also I need to have information about how many wells I have to plug, how many platforms I have to scrap, how many pipelines I have to remove, etc. Okay. And finally here we don't come with much, but we actually come with NPV, okay, IRR, break-even, oil or hydrocarbon price, and break-even time. Okay, to make my evaluation. But basically I have that diagram. That's the value chain of my field. Okay, and then initially some boxes are empty. So to make my valuation, I have just to make some assumptions. But with time, I'm giving more and more information on each one of these boxes. I'm getting more and more information for all of these factors. And then the evaluation is becoming more and more precise. More and more. Okay. So let's take very briefly. I want to make a brief. We don't have much time, but let's make a brief description of what do we have in each expense. Okay, capex. We have engineering studies. Okay, and that's basically salaries or consultants. Or contractors. We have the processing facilities. Then inside of here we have the separators. We have pumps. We have compressors. We have water injection in system. We have gas injection. We have water treatment, water, oil, and gas treatment. still big enough? Yeah. Okay, then we have to be on the offshore structure. Where we have the cost of the platform. Can be I have FPSO, can be that I have a TLP. We're going to see later some more details, like GBS, gravity base structure. Okay, so that means manufacturing, moving to place, deployment, mooring, how to hold it in place. And also we have inside, we have the living quarters. Okay, how many people are going to be living there, the requirements for toilet, for kitchen, etc., auxiliary equipment. Okay, the power system. Okay, then we have, let's see if I'm forgetting something. And here we're including, on all of these, we're including installation. Actually, let's go design, manufacturing, and installation. Okay, then another thing which is worth mentioning is the subsea system. And then we have the template. Typically we put here the Christmas tree. We put the flow lines. We put the pipelines. We put also the metering. We put risers, umbilicals, control system, okay, and finally, it's not a complete list, but at least the most important, it's the export system. Okay, if I want to make a pipeline that I have to couple to an existing gas distribution network, if I have to buy tanker, if I have to buy an LNG tanker, if I have to do that, part is included there. Now let's go a bit on the Drillex. We are just going to finish, just be a bit patient. The main expense here is the drilling rate of the vessel, drilling vessel. That's a big part of the expenditure. I'm renting a vessel to make the drilling, and that has to be paid even if I'm drilling or I'm not drilling. So I need also the materials, and typically they are required for well completion. Okay, all the casings, tubings, everything that goes inside the well. But also materials that I need for drilling. I need additives for the mud. I need the cost of the wellhead. So I include here tests while drilling. Okay, that is called drill stem test, DST. We have logging. We have pressure test. And then we have also drilling tools, bits. Okay, roughly said, that's more or less everything.
How about the sampling?
Yeah,
Sampling?
yeah, that's well, that is done through the ST, but you can do also other kinds of sampling.
What about core sampling?
Yeah. Coring, yeah, let's call it sampling, just simply said. Okay, now comes OPEX, and OPEX is interesting. OPEX, we have, you know, the salaries of, you're going to be employees, right? So salaries of the workers. You need to pay the insurance. You need to pay maintenance. You need to pay for, yeah, that's in maintenance, equipment. You need to pay for well intervention. Power that you need for heating, that you need for controlling the equipment, that you need for compressing, that you need for pumping. And then you need production chemicals. That's something we are going to discuss later. But we need a few chemicals for all kind of reasons. We need, for example, hydrate inhibitor. We need the emulsifier. We need a wax inhibitor. Corrosion inhibitor. Okay, etc. We need also to perform pigging. We're going to talk about that also a bit later. And transportation and export. Okay, and then we go to oh, something we forgot here. Okay, that what do we forget? What do we forgot here? The tax, right? You cannot forget about tax. Not in Norway, especially. Tax and royalty. Okay, and finally we have ABEX, abandonment expenses, that we have well plugging, removal of facilities, structure, pipeline, cleaning, and all kind of things. Yeah, scrapping, cleaning, etc. Okay, so after we have that picture, okay, we have to come with all of that information. We have to come with a single number. So we perform what is called cash flow calculations. It's like if you visualize that, we have, for our project, we have a scale, okay, where we have in one hand we have revenue, and in all the other side we have all the expenses that are tax, capex, drilex, opex, all kind of things. And we have to make sure to be a balance, to make a proper comparison between these two and find how do they compare. And that we perform by making cash flow calculations. And they are typically performed twice a year or once per year. So I have here first put the year. It's like accountancy, okay? Maybe we saw it in Videregoena school. Okay? So we start first with accountancies made. There are some variations, but typically made by the end of the year. You say that's the end of a year, the end of year 1, 2, 3, and 4, yeah, and so forth, all the years that your project lasts. Then you have to calculate the revenue. Typically you have the volumes, okay? You typically have gas or oil volumes that you have produced during that year. Based on a given price, you calculate the revenue. Okay, it can be multiplied. Typically we use a constant number. For gas, that's typically we operate in contracts. So we negotiate a fixed number on the price of gas with the customer. For oil, then you have a fluctuation, and typically you just assume a constant value, and then you start changing it to see how it will affect your project. Revenue, and then we put all the sources of expenses, which are capex, opex, then you have drillex, then you put here, let's put these three only, not include apex. Then we have the cash flow or the net income. Let's make to make it simple, there is another course in this department called Petroleum Economics. How many of you have taken this course? Yeah. So there you can see all details, exactly how tax is calculated, depreciation, the effect of... here, I just want to give you a very, like say, a very rough idea. How do you calculate NPV? Okay, what is included? Basically revenue and income. But it can be, if you want to make it more realistic, you have to include other things. Okay, you have to include tax, you have to include depreciation. For that I really recommend you go to that course, okay, Petroleum Economics. But here we're going to keep it slightly simple. So net income, we say revenue minus, or maybe call it cash flow. Not really the income, but it's the cash flow. Revenue minus the expenses. Okay. And if we plot that, so initially, for example, you won't have any revenue. All of these will be zero. It's only when you start producing that there you will have a number. Okay? Initially, you won't produce any volumes, but then you will have production of oil and gas. Capex is the contrary. You have initially a lot of expenses, you have to buy a lot of things, and then typically you don't have any expense. Then OPEX, the same thing. Typically I have no OPEX, or if I have some activity I might have a little bit of OPEX, but typically I don't have until I start production. And drillex the same. I have drillex initially, and I might have even some drillex going to the beginning of the project, but then I have no drilling. And that depends a bit what is the strategy of developing the field. I might say I want to do with pre-drilling, means all wells they have to be in place before producing. And in that case there is a very clear split between where I have drillex and when I don't have drillex. Or I can have it gradually, that I put some wells in production, they start producing, making revenue, and then I start and continue drilling the rest. Okay, so if you make a plot of this cash flow, okay, in US dollars or in NOK, we are going to make our calculation in US dollars versus time. You will see which is, and remember this is discrete, we're making it year by year. You will see that initially is negative. Okay, then at some point I start production and I start to get some production, then it becomes big. Okay, and then when I have the decline, then I start to go lower and lower. And the fraction of that value will be part of it will be revenue, but then you will have the deduction of OPEX, and here you have the expenses, the capital expenses, mainly made by the capital expenses. So here is negative, all of this area. If we are going to make it with a curve, we have a change. Well, it's almost time. Yeah, so you see something, a difference between, and I think that is discussed in the chapter by Dake that you have in the references, that for an offshore development, you have a very deep, at the beginning, during the first phase, you have a very big expenditure. You have a very big negative cash flow. And then it starts to go up very quickly, and then will go like that. So that's typically offshore. But onshore, it can be that I have a much prolonged investment and much less, and then might be that my recovery, my revenue is also a bit less. So that's typically onshore. Okay. And that is because for what we discussed earlier, that when you have an offshore system, you have to have everything in place to start producing. It's not simply that you put 2 wells in production, connect it to a separator, and start making money. You have to have everything in place from the beginning. So they want to make this part extremely, extremely short between the start of the project, the start of the project and the start of production, such that you can start to get revenue relatively early. Okay? Now, some people compute here the cumulative cash flow. I'm going to take a few minutes, if that's okay with you. Cash flow, where it's simply summing. This one will be this one, and this one will be the previous plus. Yeah, let me make it. I think I use colors here. Okay, the previous plus the current. Okay. But really that's not, because they are made in different times, right? So the value of money is different if I have it in year 2, in year 3, year 4. So what we use typically for oil and gas projects, we have to discount that number. The cash flow we first discounted, okay, so it's DCF, discounted cash flow. Let's put it here. Okay, where you know that the present value is equal to the future value times 1 over 1 plus and a rate, a discount rate, that is equivalent for internal for the company. If they took that money, invested in the bank, invested in other assets, they will get some value. That's a value that they want to get at least the same return. And here you have the year counter. Okay, so that's the discount rate. That depends on the company, but typically it's a number between maybe 6 and maybe 15%. And T is the year counter. That tells you if you're receiving $10,000 in 10 years, it will have a lower value than if you receive it in 5 years. Okay, so that's how I calculate the discount cash flow is equal to the cash flow times 1 over 1 plus I to the power of T. And simply the NPV is just simply the sum of all of those from I equal T, from T equal 1 to the number of years. Cash flow of I of T. Okay, so basically in our column we have the discounted cash flow, and for after all of it I make the sum I make the sum of all of these DCF, and I found the net present value of the project. Okay, so I think that's all I have time now to tell you, and we, continue tomorrow. Tomorrow we are going to have the first part of the lecture will be you're going to present. Those of you who are still missing, who is missing? Who still has to present? Wow, all of you you're not in the same group. Okay, one of each group just leave. 1, 2, 3, 4, 5.
There's another one missing.
Okay, so it will take like 1 hour and a half. Okay, during the first 1 hour and a half we take that, then I will do, but not very much, and then we are going to review the exercise 1 in class. Okay, the answers of exercise 1. Okay, any question before we close? No. Okay, see you tomorrow.